In this problem, we would like to find an equation for the osculating plane to the spiral helix at a point. So when you have a space curve at a point, there is a unit tangent vector, there is a unit normal vector that points in the direction that the curve is bending, and these two are perpendicular. And then you have a third vector which is perpendicular to both of these, that in this case would be sticking straight up out of the screen or maybe down into the screen. So you have these three vectors that are mutually perpendicular. So that's a right angle and that's a right angle, 3 dimensions here. And they make what's called a TNB frame or a Frenet frame or Frenet-Serret frame. And this tells you, the tangent vector tells you what direction the curve is headed. The normal vector tells you what direction the curve is bending. And then the binormal vector, which would be the one in this case sticking straight up out of the screen, that vector is perpendicular to the plane that the curve is in near this point. And that plane is called the osculating plane. So as a plane moves through space, if you pick a point on the curve and you zoom in on the curve, then the curve is for the most part in a plane. And that plane is this osculating plane. If the curve is a plane curve, then the osculating plane is just the plane that the entire curve is in. Okay, well, a spiral helix is not a plane curve. It's a curve in 3 dimensions, but at any point on the curve, there is going to be this osculating plane. And we want to find the osculating plane at a point pi 5, 0, and we've analyzed this spiral helix in previous problems and videos, and the time t when the helix is at this point is pi over 4. We can see that from just setting 4t equal to pi. And then the unit tangent vector is r prime of t divided by the magnitude of r prime of t. And after plugging in pi over 4, we got in a previous problem 1 over the square root of 29, 2, 0, negative 5. And then the normal vector, the unit normal vector n, is t prime of t over the magnitude of t prime of t. And we also calculated this one. It was n of pi over 4 is 0, negative 1, 0. And lastly, we also calculated the binormal vector, b, which is t cross n, and we evaluated that at pi over 4, and we got 1 over the square root of 29, negative 5, 0, negative 2. So these are all unit vectors. Now we would like the equation of the osculating plane. So if you want the equation to a plane, you need two pieces of information. You need a point, and you need the normal vector to the plane. Well, if this is the osculating plane, then the normal vector to this plane is this binormal vector. And the point in the plane, we have the point pi 5, 0. So we have all of the information. So this b vector is negative 5 over root 29, 0, negative 2 over root 29, and the point is pi 5, 0. So the equation of a plane that goes through a point x0, y0, z0 with normal vector ABC is the plane a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And so in our case, that would be negative 5 over root 29 times x minus pi plus 0 times y minus 5 plus negative 2 over the square root of 29. So I should really just make that a minus. Minus 2 over the square root of 29 times z minus 0. And that's equal to 0. Let's clean this up a little bit. Let's multiply everything by the square root of 29. Let's multiply everything by negative square root of 29. So we get 5 times x minus pi plus 2z equals 0. And that means 5x plus 2z is equal to 5 pi. So there is no y component in the equation of this plane. 5x plus 2z equals 5 pi.